Hey everybody. So this time we're going to be looking at a handout that I'll publish along with this. It'll be in Blackboard as well as in the email I send you with the link to this video. So last class we worked on finding duals, and they were pretty neat. We went through an example last time of this handout. I hope you looked at it, where we worked on constructing duals from a primal linear programming problem. And then once it was constructed, we did an experiment and solved each side. So today I would just like to talk a little bit more about the relationships between primals and duals. So I have a handout here that has a lot of this information. The very first thing is what we ended on last time. It's called the dual theorem. Some people call it strong duality. It says if there is an optimal, if it does exist, which is once again an important thought, if the optimal does exist, then at the optimal, the primal and dual objective function values are going to be equal, right? And we saw that last time, that they will be equal. The z and the w were in fact equal. If we go back and look at this example where we had solved them, the objective function values, let's see, the objective function value for the optimal primal was z equaled 24. For the optimal dual, once we hit the optimal, the objective function value was 24 as well. So that's the very first fact we get there. So it's pretty awesome that if you do have an optimal, you'll know that if you find one or the other, you will know what the optimal objective function value is to both, because they will be equal. Okay, that is a powerful thing. Another powerful thing is weak duality. Okay, weak duality says this, that first let's assume the LP is a max and the primal is a max and the dual is a min. You could flip this and flip all the words, but any feasible point, so any basic feasible solution to the LP will have a function value z. It'll be smaller than or equal to any feasible point in the dual. So less than or equal to. When would it be equal? It'll be equal to at optimality. At optimal. Okay? So does everybody understand what I'm saying? So let's go back to our example from last class. If you look at each pivot of the dual, these are the only two feasible ones, because right here we were getting into the phase 2. And it only took 2 pivots in phase 2. But right here, just a random feasible point had an objective function value of 24.67. Okay? A W of 24.67. Any feasible point over here was 0, 20. Those are all smaller than all the feasible points of the dual. These don't count in phase 1 because these are not actually feasible points. You're trying to push to feasibility through phase 1, remember? So once you get feasible, any feasible point will have an objective function value that's bigger than these. So the way we worded it was the primal is smaller than the dual at every feasible point. Smaller than or equal to, when is it equal? When they're optimal. Okay? That's another just relationship between them. That's a weak duality. This gives us the ability to make upper bounds or lower bounds if you flip them into the max. Okay? It's actually really powerful. I told you last time. Actually, I told you when we discussed degeneracy that airline scheduling problems are really hard to solve. They have a whole lot of degeneracy in them, and they take hours and hours and hours and hours to run the code to solve them. Take a long time to model them. They're really hard. They usually don't come up with the optimal. What they do is they run some dual pivots, and they run some primal pivots, and they come up with upper and lower bounds on where the actual solution is. And this allows them to get a good enough answer, because it would take days for them to get the actual answer, days of computer runtime, because the complexity is so bad on those problems. But using this to create upper bounds or lower bounds, they can kind of sandwich in the actual value and make good choices. Okay? Now there's another relationship between duals and primals, and it has to do with things are being bounded or unbounded and whether things are feasible or not. So y'all remember back in like the very beginning when we were drawing graphs, you could have constraints set up to where your LP was unbounded. The feasibility region went on forever. But you also could have constraints to where things were not feasible. Like say we had to be greater than this line or less than this line. There's no feasible point. You can't solve this LP. There's actually a relationship between duals and primals that are unbounded or unfeasible. And the relationship's just like this. If the primal is unbounded, then the dual will be infeasible. And vice versa. If the dual is unbounded, then the primal will be infeasible. So that's useful in that, say you have a really, really hard primal problem to solve, and you just can't solve it. So you convert it to a dual, and you work on solving the dual, only to find out that the dual is unbounded. It has a direction of unboundedness, and it can improve forever. Well, then that would save you from doing any more work, because you automatically know the primal is infeasible. I can't do the primal problem. The original problem is not solvable. So just this relationship's kind of interesting. Okay. One more interesting note on that. Before we went into this, we spent time on sensitivity analysis. And remember, while doing sensitivity analysis, we talked about shadow pricing. And shadow pricing, remember, was the unit increase or the unit improvement that we would see from each unit increase on a right-hand side for each constraint. And so once you actually solve for the dual, so say we solve for the dual, let's go back to this one, and we found that at the optimal, y2 had a value of 1/2 on this problem that we did last class. That means, if I can scroll back up to the original, primal, constraint 2, the right-hand side here, has a shadow price of 1/2. Okay? The y1 was 0, so this one has a shadow price of 0. Improving this by 1 gains you nothing. Okay? So, once you have the dual solved, each variable's value is the shadow price of that constraint. So y3's value is the shadow price of the third primal constraint. Okay? So, now here's a very, very powerful idea that we're going to talk about. And I've mentioned this, and we've kind of led to it. I've teased with Caleb about complementary slackness, where our slacknesses complement each other. Sadly, that's not it, but it's a very, very powerful math idea. Complementary slackness. Okay? I had a professor once who had a very hard time saying that. He was an American, but every time he tried to say complementary slackness, he would say complementary snackness, and he would just bust out laughing and die laughing. It was really funny if you were there, but I'm sure it would be annoying over if I did that every time over the video lessons. Maybe if we were in person, we could call it complementary snackness if we wanted to. But let me give you the formal definition of this thing. What it says is, say we have some x value, and let it be a feasible primal solution. Okay? And we have a y value. Let it be a feasible dual solution. Of course, they're going to have slack variables, and we'll call the ones for the dual the xx variables, or the extra variables, xs. Okay? So we know that the x is the optimal solution, and the y is the optimal for the dual. We know that we're optimal if and only if these equations hold. If and only if. If you take the slacks from one problem, dot product them with the variable from the other problem, and they equal 0. Same thing, the slacks or the excess variable from the dual, dot product them with the variables from the primal, they should equal 0. Okay, do you see that? That's kind of interesting. It's called complementary slackness because these are the slack variables. And the other problems, sometimes called the complement problem, the complementary problems, the primal and the dual, they're other problems slacks if you multiply by the variables, will always equal 0 if and only if you're at optimal. Okay? If and only if you're optimal at that point. Okay? So some people use this as an optimality condition to prove they have an optimal when they're solving problems that are extremely difficult and sometimes you're not sure when you have the optimal. So they can do this. This is actually part of something called, you could Google this, a KKT point. KKT conditions. KKT points means you have the optimal, named after mathematician Karush Tucker. It's 3 mathematicians, and one of them was a student working on their master's degree that came up with this, and the other 2 were their advisors. It just says that when you're primal feasible, dual feasible, and you have complementary slackness, then you know you have an optimal point, or a KKT point. So that's a pretty powerful idea, used a lot in higher level operations research. Okay, so let's actually play with this and see if this holds. Okay, so I think that's all on this page. Let me go to the next page. So here's this example. Okay, this is the primal problem. I've written the dual problem, and this is a problem we've actually already solved earlier in the semester. We got the objective function value to be 280, and this is the optimal point. So the optimal over here, W, better be 280 because they're LPs, so they are equal. And we see this is the optimal point. Now notice these right here are the X's, right? And these right here are the slacks. So let me kind of label those. X's and the slacks. And over here, these are the Y's, and these are the excess, or the slacks. So literally, we should be able to check that E dot X equals 0. And that won't be too hard. You could probably check just by glancing. Because look, X2 would be multiplied by E2. And it's 0 times 5 is 0, right? 2 times 0 is 0. 8 times 0 is 0. So if I were to write this out, probably should write it in the other order, but it doesn't matter. We'll call that transpose because it should be vertical. And if you just multiplied these out, you'd have 2 times 0 plus 0 times 5 plus 8 times 0. Of course, that's 0 times 0 plus 0 plus 0. That's just 0. Now let's check the dual variables times the primal slacks. What'd you get? 0 times 24 plus 10 times 0 plus 10 times 0. So complementary slackness holds here. That's how we're sure we're at an optimal. And we better get this because it's if and only if. If we are at an optimal, these will be 0. If these are 0, we are at an optimal. So there's an example of complementary slackness. You could check this on the example that we worked last class, or that I provided you last class. It already has a dual and a primal solved. You could check the solutions to see if complementary slackness holds. We could probably attempt to do it in our head. Let's see, which one are the slacks? I have 3 slacks. So only 2 variables, 3 slacks. So the slacks here are 2, 0, 0. What's the Y value? Y1, Y2, Y3. Oh, that's not the optimal. I was like, why is it not working? There's the optimal. 2 times 0. 0 times a half, 0 times that. And then the slacks here, the excess variables, are 0, 0. And if you go to the dual, 10 and 4 times 0 times 0. So yes, complementary slackness holds at the optimal. Okay, only at the optimal. Alright. So now this provides us with a very powerful thing to use. So here's how we can use complementary slackness to find a solution sometimes. Say we know either one. We know the optimal point for the dual, or we know the optimal point for the primal. And we'd like to be able to generate the complementary solution, the solution for the other one, the dual or the primal. We can use complementary slackness to do this. Okay? So let me kind of talk you through this idea. So let's go to I think the example that we just did. So let's pretend that we knew the primal solution. We know the primal solution was z equals 280, and this was the answer right here. And remember, this is x1, x2, and x3. And these are the slacks. Slack 1, slack 2, and slack 3. Okay? So we knew that, right? So then, if we wanted to find the dual solution, that means that anything that has value here would have to have a matching excess or variable equal to 0. So x1 and x3 have value 2 and 8. So that means xs1 and xs3 better take on value 0 so that complementary slackness will hold at the optimal. Same thing here, slack 1 takes on value. So in the dual, y1 better equal 0 so that complementary slackness can hold at the optimal. Okay, now we're pretending we didn't know the answer, but right off the bat I know that these three values have to be 0. Okay? Now, since E1 and E2, now stay with me here, since XS1 and XS2, the slacks on 1 and 2 of the dual, equals 0, that means that the constraints 1 and 3 are binding. Remember what binding means? Graphically speaking, if I could draw the constraints out, that means that solution is at the intersection. Both of these are tight. There's no excess. So this constraint right here and this constraint right here would be binding. This one's slack. I'd have to have some slack variable to bring this down equal to this line here. So these two are the binding ones. Because their excess is 0, that means I know that these constraints are binding, or the other word we used was tight to explain that. Since they are tight, I know then that this is constraint 1 and this is constraint 2. You can go back and look at the example. I can scroll up. Constraint 1 and constraint 3. Sorry, not 2. I know that they're going to be equal to their values. Equal to 60 and equal to 20 because they are tight. Now look at this. I know that these y1s are set equal to 0, right? So I could ignore that and just pay attention to this right here. Now, anybody that passed Algebra 1 should be able to solve this. This is just a 2x2 system solve. You could use row reducing, you could use substitution, elimination, you could use, anything fancy you wanted to use to solve this 2x2 system. And if you solved it, you'll see that y2 has got to be 10, y3 has got to be 10. And so I could come up with the dual solution. I know the dual solution, it had a y1 value of 0, and the y2 value's got to be 10, and the y3 value's got to be 10. Now, I may not be able to find all the excess variables. I knew 2 of them were zeros, but I'd have to solve another system to find the other excess variable. But for now, actually that would be pretty simple just to plug in all that I know, since I know 5 of the 6 values. But that's overkill right now. So we can use that to find a dual value. So that's actually pretty powerful and pretty awesome. So these are all really, really important, really, really strong relationships between primals and duals. And there's a lot of powerful mathematics built off of these ideas, specifically built off of complementary slackness. Having primals and duals, you can generate the other solution. Some people make a game of trying to get them both feasible. And meeting complementary slackness, if you get them both feasible and meet complementary slackness, then you have the optimal. That's another way of solving some LPs. It's not quite straightforward or systematic, but sometimes it may be faster or easier. There's a whole lot of creative algorithms created out of using complementary slackness because it is so powerful. Alright? And all these other relationships on the handout are very powerful to use along with this. Being able to create upper and lower bounds, understanding boundedness and feasibility, These are types of questions I may add as short answer questions, okay? But complementary slackness is extremely powerful, okay? So I think that's all I want to cover today. So we'll stop right here. Next time I'll show you something that uses these relationships, and it's called the dual simplex method, which is another really awesome thing. If you could solve a if you could do the normal simplex, that's pretty cool. But the dual simplex is another way of solving linear programming problems using all of this understanding that we have built over the last 2 days. All right, y'all have an awesome day. I will see y'all next week.